Hi everyone. Today I'm going to be talking about the question 7 from our textbook exercise that we tried last week in class. So part A was quite straightforward. It was a binomial expansion of 2k take 1 to the power 5 and 2k plus 1 to the power 5. And I'm sure you'll be able to see if you do the working that that's the solution there. Now the hard bit was part B. We were required to prove the following proposition. N to the power 5, take n, is divisible by 240 for every n which is a positive odd number. So I've written it like this. So our base case, when n equals 1, we substitute 1, we get 1 to the 5th minus 1 is 0, which of course is divisible by 240. 0 divided by 240 has no remainder. And so our value of proposition 1, P1, is true. Now our assumption. I've assumed, because we're dealing with odd numbers, I haven't assumed pk, I've assumed the odd number 2k minus 1, where k is an integer. So in the case where k equals 2, this would evaluate to proposition 3, the next one in the set of values. In the case where k equaled 3, then 2 3s, 6 take 1, it evaluates to 5. So that's an appropriate way to express just odd numbers by using a value of k, which is a natural number. In other words, this proposition would read 2k minus 1 to the 5th, take 2k minus 1, is a multiple of 240. I wrote 240 times m. M is an integer, of course, if it's a multiple. Now, expanding out 2k minus 1 to the 5th was done above. It was already there. So I copied that out, and we still have at the end here subtract 2k plus 1. So the negative 1 and the positive 1 cancel, and then 10k take 2k becomes 8k. So this statement here, which I've labelled equation 1, this is really the statement of my assumption. Let's move into the inductive step. We have to now prove the next odd number after 2k minus 1. So odd numbers jump up in by 2. So the next value is 2k plus 1. Again, k is still an integer, which is greater than or equal to 2. So this is what my required to prove looks like, that 2k plus 1 to the 5th minus 2k plus 1 is a multiple of 240. Now I've just put a different integer q instead of m because it wouldn't be the same value, the same multiple. So I began on the left hand side. 2k plus 1 to the 5th, we expanded that out in part A, so there it all is down to the plus 1 there. I have minus 2k minus 1. The positive and negative 1 subtract, and this time 10k plus minus 2k is 8k. Now this line here is almost but not exactly the same as my left hand side of my assumption. The trouble is I have a negative in the 80k to the 4th and a negative in front of the 40k squared, but down here I've got positives. So if I want to copy this line down and make that negative, I would have to compensate by adding 160k to the 4th over here. And if I want to change that from positive 40 to negative 40, I'd have to compensate, balance the equation by adding 80k. So effectively, negative 80k to the 4th plus 160k to the 4th is the same as the positive 80k to the 4th that was on the previous line, and the same here with the k squareds. Now this much to here, is identical to the left-hand side of my assumption. So all of that can be replaced by 240m from my assumption, which was labelled equation 1. I still have plus 160k to the 4th plus 80k squared. We could factor an 80k squared, leaving 2k squared plus 1. And I've paused here and called this equation 2. Now this is where we got to in class, and this is where we sort of ran into a bit of a brick wall and we weren't quite sure how to proceed. So I can see that I have a multiple of 240 in this term. Fine. Over here I have a multiple of 80, but I really need that to be a multiple of 240 if I'm going to complete the proof. That means that k squared must be divisible by 3, or perhaps this term, 2k squared plus 1, must be divisible by 3. And it wasn't obvious to me whether that idea is true. So I started playing around with the numbers. I listed the values of k from 2 onwards for every integer of k, just as we had said here, k is a natural number greater than or equal to 2. I then calculated k squared, so 2 squared is 4, 3 squared is 9, and so forth. I've highlighted the ones in this list which are multiples of 3. So not all of them are multiples of 3. I then calculated 2k squared plus 1. So 2 4s are 8 plus 1 is 9. 2 9s are 18 plus 1 is 19. 2 16s are 32 plus 1 is 33, and so on. And then I've highlighted the ones in this list which are multiples of 3. Now this is where I had a light bulb moment. Either k squared is a multiple of 3, in the case where k is 3 or 6 or 9, or 2k squared plus 1 is a multiple of 3 in the other cases. In the case when we are 1 more than a multiple of 3, or the case like this when we are 1 less than a multiple of 3. Now that's not a proof, that's just a list of numbers. I mean, I went down a little way, but certainly that's not a proof. That's just noticing a pattern. It's our job to prove that is true. And this is the bit that I did to do that. So I've made a statement here. If k squared or 2k squared plus 1 is a multiple of 3, then we could factor a 3 from those, combine with the 80 to become 240. Both terms then would be a multiple of 240 and our proof would be complete. So our job now really is to prove that k squared is a multiple of 3. Now that's not too bad because I've just, if I go back to here for a moment, you'll see that I'm looking down here at the values of k, and I'm trying to find a systematic way of representing those. So if k equals 3, well that's 3 times some integer, which I've called f. If k equals 6, that's still 3 times an integer. Same. So I've said k could perhaps be represented as a multiple of 3. That's my ones here that work out here in this column. So if k is 3f, k squared is 3f squared, which is 9f squared, which is clearly a multiple of 3. Easy. But what about if we're dealing with these pairs of numbers here? Do you notice that these pairs of numbers could be either 1 less than or 1 more than a multiple of 3? So I've taken the case where k is 3f take 1. Then my expression, which I'm interested in, is the 2k squared plus 1 expression. So 2, instead of k squared, 3f take 1 squared. Expanding that and then simplifying. Notice here that 2 plus 1 would be a 3, which means I can factor a 3, and this expression, 2k squared plus 1, is definitely a multiple of 3 if we are 1 less, if k is 1 less than a multiple of 3, like if k is 2, or if k is 5, or if k is 8. Now there's one more case to consider, and that is the case where k is 1 more than a multiple of 3. Again, I'm interested in the 2k squared plus 1 part of my original proof. So I substitute this, I expand. Again, the 2 plus 1 is 3, so there is definitely a multiple of 3. Now that was the bit that eluded us. We didn't see the pattern here in class, and it must admit it took me a little while, and I ended up playing around numerically here to see, and it certainly was suggestive of a pattern continuing, but this is the proof of it here. We have to consider the case where k is a whole multiple of 3, or 1 less than a multiple of 3, or 1 more than a multiple of 3. Each of those is like a very simple little direct proof. And then in those 3 cases, which covers all possibilities, we can then make the statement either k is 1 less or a whole number multiple, or one more than a multiple of 3. In all cases, this term had a factor of 3. So our equation, which I labelled 2 back up here, this equation, there would be a multiple of 3 in this part of the equation, no matter what the value of k. Either this part is a multiple or this part is a multiple. In which that means that there is a factor of 240, which means that we have proved proposition 2k plus 1. And finally, here is my conclusion. So if p 2k minus 1 is true, we have managed to prove the following case, p 2k plus 1. As p1 was true, then by induction the proposition is true for all odd number values of n. Thanks for watching.